a crew wakes inside a habitat beyond Earth and begins what seems like any other day. The lights come on, air moves through the rooms, and water runs from the taps while the people aboard prepare for work. The habitat might be orbiting Earth, standing on the Moon, or buried beneath the surface of Mars. Wherever it is, almost everything keeping its residents alive still reaches back to our planet. Food arrives from Earth, so do medicines, replacement parts, and much of the machinery needed to keep the habitat working. Engineers on the ground study faults, factories build new components, and cargo vehicles carry them across the distance. Then, one day, a scheduled message does not arrive. At first, that would not seem unusual. Antennas fail, solar activity interrupts signals, equipment loses alignment. The crew would check the communication system, send another message, and continue with the work already planned. But Earth would not respond. Even then, the habitat would not fail immediately. Its lights could stay on, its fans could continue moving air, and its water systems might keep recycling what the crew had already used. Stored food could last for months, while trained people repaired equipment with the tools and spare parts already aboard. So the first question would not be whether they could survive the day. It would be how long they could continue once every repair began using something that Earth could no longer replace. An orbital station might have excellent water recycling, but almost no way to manufacture a new pump. A lunar base could extract ice and oxygen from the ground, yet still depend on imported electronics and machinery. Mars offers more raw material and more room to build, but every serious failure would unfold months from physical help. And lasting for a few years would still be very different from building a society that could continue indefinitely. Farms would need to survive bad harvests. Workshops would have to replace the machines inside other workshops. Children would need to be born and grow safely in environments where no human population has ever lived before. At some point, the question stops being how long the supplies will last and becomes something much larger. How much of Earth would people have to rebuild before they could truly survive without it? By the end of this video, you will understand how long humans might endure in orbit, on the Moon or on Mars if Earth stopped supporting them, which limits would arrive first, and what would have to change before an outpost could become a genuinely independent human settlement. If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. A sealed habitat does not fail like a spaceship in a movie. There may be no torn hull, no screaming alarm, and no sudden rush of air into darkness. At first, the people inside could feel almost normal. The walls still hold pressure, fans move the air, lights come on, water runs from a tap. Breakfast may look disappointingly familiar. That calm is possible because several life support loops already do much more than most of us realize. Water from breath, sweat, and washing can be collected and cleaned. Filters can remove carbon dioxide from the air. Stored oxygen can cover short gaps, while other equipment can recover oxygen from water. So the opening emergency is not necessarily measured in minutes. If the habitat remains sealed and its main systems keep working, the first realistic planning horizon may be measured in months. That sounds reassuring. It is, a little. But a loop is not the same as complete independence. No recycling system returns every drop of water. Filters wear out. Pumps have bearings. Seals crack. Sensors drift. Chemicals used to clean the air are consumed or contaminated. Even a small daily loss becomes serious when nobody can deliver another container. Food makes the limit easier to see. You can clean yesterday's water and breathe oxygen made from it again. You cannot keep eating the same meal. A habitat may carry months of food, perhaps more, but every package moves in only one direction, from the shelf to the crew. Then there are the dependencies hidden behind the walls. Replacement parts, medicines, lubricants, computer boards, spare valves, the exact tool needed for one awkward fastener placed where no human hand can reach comfortably. A habitat may seem self-contained, while depending on a long chain of factories, launch vehicles, technicians, and warehouses back home. That is why how long can they survive has no single answer. It depends on what broke, what remains stocked, and which loops can still be repaired. Air might be stable while food declines. Water might be plentiful while one cooling pump threatens the electronics. The first months are therefore less like waiting for rescue after a crash, and more like managing a house where every shop on Earth has closed. Nothing has to kill you today. The danger is that one ordinary shortage eventually becomes the thing you cannot work around. So which supplies run out first, and which machines must keep working every single day? A space station already treats yesterday's waste as tomorrow's supply. That sounds grim until you realize it is one reason the crew can think in months rather than hours. Water is the strongest loop. Moisture leaves the body in breath and sweat. It also leaves through washing and the toilet. Machines collect much of it, remove dissolved waste, kill microbes, and test the result. The water returns clean enough to drink. It may have passed through another astronaut yesterday. So has plenty of the water coming from an ordinary tap on Earth. Nature has been recycling the same water for billions of years. The station simply does it inside a smaller box. The recovery is good, but never perfect. Filters need replacing. Pipes hold a little water. Some escapes with trash or through small losses. Fresh water still has to arrive from Earth, just far less often than it would without recycling. Part of the air moves through a loop as well. The crew breathes out carbon dioxide, and machines pull it from the cabin. Other equipment can split water into oxygen and hydrogen using electricity. The oxygen returns to the crew. On some stations, hydrogen can react with captured carbon dioxide to make water, recovering another portion of the system. You can think of it like washing the same set of dishes each day. If the sink, soap, and drain keep working, you do not need a new plate for every meal. But you still need replacement soap, seals, sponges, and the occasional new dish. The loop reduces the supply problem. It does not erase it. That difference buys time. A missed delivery does not mean the air vanishes that evening or the taps run dry by morning. Crews also carry reserves, and they can reduce use when trouble begins. Months become a reasonable first scale because the fastest consumables are already being recovered. Yet the loops depend on pumps, valves, sensors, filters, power, cooling, and people who know how to repair them. Food does not return after it is eaten. Spare parts do not grow inside a cabinet. The crew can reuse molecules, but not the industrial world that built the machines around them. And beyond those first months, survival begins to depend on how much of that world can fit inside the station. A station can keep breathing and still run out of time. The deadline may be sitting in a cupboard, disguised as the last compatible seal for a water pump. That makes survival less like watching one fuel gauge and more like managing a crowded kitchen during a long storm. Flour may last for weeks, fresh food goes first. A broken refrigerator changes every other plan, and the one spare fuse nobody thought about can suddenly become more important than everything in the pantry. Crews track supplies in much the same way, though the list is far less forgiving. Every meal removes food from storage. Every medical treatment may use something that cannot be replaced. Clothes wear out, batteries weaken, tools break. Even a small repair can consume tape, fasteners, lubricant, cleaning cloths, or a spare part that was meant for another job. The awkward part is that you rarely know which item sets the final date. A station might have plenty of food, but too little repair capacity. It might have the right component, but no safe way to reach the damaged equipment. A replacement may fit perfectly, while the tool needed to install it is broken. The final limit often hides in the least glamorous cabinet. This is why the first believable horizon is measured in months. Some essential cycles can keep operating for a long time, and stored supplies provide a cushion. Crews can ration food, postpone experiments, share equipment, and turn damaged hardware into parts for something more important. Human beings are very good at making do when the alternative is worse. But improvisation spends resources too. Taking a working unit apart to save another one leaves one less working unit. Using a medicine today means it is gone tomorrow. Each repair changes the inventory, and each change narrows the choices available after the next failure. So the station's true clock is not mounted on a wall. It is spread across thousands of objects, each aging at its own pace. The deadline arrives when one necessary thing can no longer be replaced, repaired, borrowed, or worked around. If months are possible with careful rationing and good luck, what would have to change before those months could become years? People have lived aboard the International Space Station without interruption since November 2000. That sounds like proof that humans can settle beyond Earth, until you look at what keeps those humans alive. The station is less like a distant town, and more like a cabin with an extremely long extension cord. Air and water are recycled aboard it. Solar panels make electricity. Crews repair equipment, grow small amounts of food, and learn how bodies change in weightlessness. Those are major engineering achievements. They've kept a human outpost running for decades. But the outpost didn't build itself, and it cannot replace itself. Every crew arrives in a spacecraft made on Earth. Cargo vehicles bring food, clothing, medicine, tools, experiments, spare parts, and fresh equipment. Teams on the ground watch the station around the clock. Engineers study strange noises, test repairs on matching hardware, and send instructions upward. Even the station's orbit needs help. Wisps of atmosphere slow it down, so visiting vehicles regularly push it higher. Continuous habitation proves that a large support system can keep people alive in orbit. Much of that system remains on the ground. You can see the difference by comparing the station with a town on Earth. A town may depend on distant factories, fuel, and trade, but it also contains workshops, vehicles, warehouses, people with many skills, and access to raw materials. If a pump breaks, someone can often make a part, find another pump, or bring one from nearby. The station has skilled people and good tools, but almost no raw material and very little room for manufacturing. NASA has tested machines that print simple objects in orbit. Astronauts have also grown lettuce, radishes, and other small crops. These experiments show that some production can happen away from Earth. They do not yet provide the calories, medicines, electronics, metals, plastics, and replacement machines needed to support a population. There is another human detail here. A civilization needs more than breathing people. It needs enough people to raise children, teach skills, care for the sick, divide labor, and recover after accidents. The station usually holds only a handful of residents. They are selected, trained, and supplied by a civilization below them. So decades of occupation tell us something impressive and limited. We know how to maintain a crude foothold above Earth while Earth does most of the heavy work. What would an orbital settlement need before it could take over that work for itself? Water is the closest thing the station has to a closed loop, and even that loop needed decades of work. A glass of water can become sweat, breath, or urine, then return as drinking water. The route sounds unpleasant because it is personal. The chemistry is simpler. Water is water once the waste has been removed. NASA says the station's current system can recover about 98% of the water used by the crew. That figure became possible after a newer device began pulling more water from the salty waste left by the older recovery equipment. 98% is remarkable. It also means the station still loses some water, and small losses keep adding up. Replacement filters, treatment chemicals, and machine parts must also arrive from Earth. Oxygen is harder. The station can split water with electricity, producing oxygen for the cabin and hydrogen as a leftover. You can think of it as taking apart a building made from two kinds of bricks. The oxygen bricks are kept. The hydrogen bricks can then meet carbon dioxide removed from the air. That second process recovers some oxygen that would otherwise leave with the carbon dioxide. NASA describes the station's present oxygen recovery as roughly 50%. So about half of that oxygen loop remains open. Some hydrogen is lost and some carbon dioxide is discarded. New water and oxygen supplies still have to enter the system. The numbers reveal an odd balance. Water recovery is near 98%, while oxygen recovery sits near 50%. Both systems work every day, around people who sleep, exercise, cook, and breathe into them. They have helped keep humans living continuously aboard the station since November 2000. That is more than a brief demonstration. It is long-running proof that engineered life support can serve real crews. But continuous habitation can hide the size of the support structure beneath it. Ground teams watch the equipment. Cargo vehicles bring tanks, filters, spare pumps and tools. Factories on Earth make every complex replacement. If a critical assembly fails, the crew can repair it only with the parts and knowledge already available, or with help sent from below. So the station has done something extraordinary without becoming independent. It has shown that a carefully supported outpost can recycle most of its water and part of its oxygen for years. It has not shown that an orbital community could build those systems, replace them, and keep them running after Earth stopped answering. A machine can run beautifully for years and still depend on a factory it has never seen. Your refrigerator may hum along for decades, but if its compressor fails, the kitchen cannot make another one. A long service proves that the machine is durable. It doesn't prove that the house can reproduce the machine. That difference is easy to miss in orbit. A crew may grow food, reclaim water, scrub carbon dioxide, and repair worn equipment. Each success stretches the time between deliveries. Each one makes the habitat safer. Yet independence begins only when those repairs no longer reach back to mines, chemical plants, chip factories, launch sites, and thousands of people on Earth. Consider a replacement valve. It may look like a small piece of metal with a modest job. Behind it sits a chain of purified ores, precision tools, seals, lubricants, test equipment, and agreed measurements. The crew might print the valve body. They may still need a material the printer can't use, a sensor it can't make, or a calibration standard that came from Earth. Making one part may depend on 100 other parts working first. Food has the same hidden tale. Growing lettuce proves that plants can live inside a controlled habitat. Feeding a settlement year after year asks for much more. Seeds must remain healthy, nutrients must be recovered, fungi, insects and crop disease must be controlled. Lights need power, pumps need bearings, and failed harvests need reserves. A salad is a good experiment. It isn't yet a food system that can restart itself. This is why endurance and independence should be measured separately. Endurance asks how long people can live with stored supplies, recycling, repairs, and outside deliveries. Independence asks whether the settlement can replace what it consumes, recover from failures, train new specialists, and rebuild its essential systems without help. That includes the tools used to make the tools. No current habitat has crossed that line. That isn't a criticism of the crews or the engineering. We built these stations as laboratories, with Earth close enough to carry the industrial burden. They were never required to become small, complete worlds. A truly independent settlement would need more than excellent life support. It would need the ability to make life support again after fire, corrosion, bad harvests, human mistakes, and ordinary wear had taken their share. So what is the smallest collection of people, machines, raw materials, and stored knowledge that could do that? It's tempting to talk about life support as though it were one machine. Keep the machine running and the people inside keep breathing. But a habitat is closer to a small town whose plumbing, farms, kitchens, and sewage works have been folded into the same building. Each part handles a different problem. Air must be cleaned and renewed. Water must be recovered from breath, sweat, washing, and urine. Food must either arrive from elsewhere or grow inside. Waste must be broken apart without letting dangerous chemicals or microbes build up. None of these jobs has the same level of difficulty. Water is the closest thing we have to a mature loop. On a station, used water passes through filters and chemical treatment. Water vapor from the air is captured too. The result can return to the crew as clean drinking water. Even urine can become tomorrow's coffee, which sounds worse before breakfast than it does after you remember that Earth has been recycling water for billions of years. Still, some water is lost. Filters need replacing. Pipes grow films of microbes. Pumps wear down. treatment chemicals run out. A high recovery rate reduces the amount that must be delivered, but it doesn't remove the need for equipment, spare parts, and careful testing. Air has its own loop. People breathe in oxygen and breathe out carbon dioxide. Machines can pull that carbon dioxide from the cabin. Other equipment can split water into oxygen and hydrogen using electricity. Some systems can combine hydrogen with carbon dioxide, recovering part of the water and producing methane. That sounds like a closed circle, but it isn't one. The methane may be discarded. Oxygen can leak through seals or leave during maintenance. Trace gases from plastics, cleaning products, and human bodies also gather in the cabin. Each one may need a different filter or chemical bed. Air is never just oxygen in and carbon dioxide out. Food is much less forgiving. You can clean the same water many times. You can't keep eating the same potato. Crops need light, space, water, carbon dioxide, and a balanced supply of nutrients. They also need time. If a pump fails in the air system, a spare pump may restore it quickly. If a crop fails halfway through its growth, no repair can give those lost weeks back. Plants bring another difficulty. A machine can be tested against a fairly stable design. A crop is alive. It reacts to temperature, humidity, fungi, bacteria, insects, root conditions, and small changes in light. 2 trays planted on the same day may not produce the same harvest. For a crew depending on them, that variation becomes part of the engineering. Then there is waste. Human waste contains water and nutrients that crops could use. It may also contain salts, medicines, microbes, and chemical compounds that shouldn't return untreated. Turning waste into safe fertilizer takes more than moving it into a plant bed. The useful elements must be separated from the harmful ones in the right amounts at the right time. These loops also lean on one another. Plants can help renew air while producing food. Waste can feed crops after treatment. Water moves through nearly everything. But joining the loops creates new ways to fail. A bad chemical balance in the waste system can damage the crops. A crop disease can reduce both food and air processing. One problem can travel. So a settlement doesn't need a single perfect life support system. It needs several uneven systems that can cooperate without collapsing together. Water recovery may work well while food production struggles. Air treatment may survive a crop loss, but only if it has its own backup. The challenge is deciding how much separation, storage, and spare capacity keeps one failed loop from pulling down all the others. And that leaves a practical choice. Which loops should settlers close first, and which supplies must still come from Earth? Food seems like just another supply to recycle, alongside water and air. But a glass of water is one substance, while dinner is a living system with roots, microbes, minerals, light, and a bad habit of dying at inconvenient times. Water is the most mature loop of the group. You drink it, release it through breath, sweat, and urine. Then machines collect and clean much of it. Filters remove particles. Chemical treatments deal with contaminants. The recovered water can be tested before anyone drinks it again. If a filter wears out, you can replace the filter. Breathing oxygen is harder, but its chemistry is fairly direct. People use oxygen and release carbon dioxide. Equipment can remove that carbon dioxide. Other equipment can split water to make fresh oxygen. Plants can help with both jobs, though relying on them adds another layer of risk. Food doesn't return so easily. A tomato is not built by cleaning yesterday's tomato. You have to grow a new plant. That plant needs the right light, temperature, water, gases, nutrients, root conditions, and time. Each need can be measured, but the whole crop still behaves like a living population. Some plants grow slowly, some become infected, some flower and never produce much food. A machine usually fails where an engineer expects machinery to fail. A crop can fail in more ways. Then there's the menu itself. People cannot live well on oxygen, clean water, and one heroic tray of lettuce. A long-term food system must supply enough energy, protein, fats, vitamins, minerals, and variety. Different crops provide different parts of that diet. They also grow at different speeds and need different amounts of space, power, labor, and water. Waste adds another loop. Human waste and uneaten plant material contain elements that crops need. In principle, those elements can be recovered and fed back into agriculture. In practice, waste also carries salts, unwanted chemicals, and microbes. Processing has to separate the valuable material from anything that could build up or spread disease. It's a little like making soup from the washing up water. The ingredients you want are in there. So are several things you very much do not want. Chemistry can sort them, but every pass has limits. And this is why closing the food loop is not one task. It means linking crop growth, nutrient recovery, waste treatment, food storage, and human health. Each part runs on a different clock. Oxygen problems can become urgent within minutes. Water shortages become serious over days. A failed harvest may not reveal its full cost for weeks or months, when the replacement crop is still too young to eat. Crop reliability is therefore as important as crop yield. A plant that produces plenty under perfect conditions may be a poor choice if one lighting fault ruins the harvest. Settlers may prefer crops that recover quickly, store well, resist disease, and tolerate small mistakes. The highest yield on paper does little good if it arrives late or all at once. Stored food remains valuable even after farms begin working. It buys time after a crop failure. It covers gaps between harvests. It also supplies foods that are difficult to grow in a small controlled space. Complete closure may demand more equipment, power, and labor than regular deliveries would. So these loops do not mature together. Water can be recovered again and again with well-tested machinery. Air can be managed through several chemical and biological routes. Waste nutrients can be reclaimed, though not without careful treatment. Food must be grown, balanced, protected, harvested, stored, and grown once more. A settlement can close much of its water loop and part of its air loop, while still importing most of its food. That isn't a contradiction. It is simply what happens when one supply is a substance and another has to stay alive. The moon seems like the obvious place to try first. It's close enough that we can see its ground from our gardens, and crews have already walked there. That instinct is sound. If a settlement needs help, distance changes everything. A flight to the moon takes days, not months. Radio messages arrive after a little more than a second. Rescue would still be dangerous, but people on Earth could watch a problem develop almost as it happened. The moon also has materials that settlers could use. Its soil contains oxygen bound inside minerals. Ice lies in some permanently shadowed craters near the poles. With enough machinery and power, that ice could become drinking water. It could also be split into oxygen and hydrogen. Those are useful for breathing, storing energy, and making rocket fuel. And there's plenty of soil for shielding. A thick layer piled over living spaces could soften the radiation that reaches the surface. It could also protect against tiny, fast-moving pieces of rock. The moon gives us raw material, nearby ground, and short travel times. That's a strong beginning. But a quarry isn't a town. The moon has no air that people can breathe. It has no rivers, forests, farms, fuel fields, or electrical grid waiting to be claimed. Sunlight is abundant in some places, especially near the poles, yet lunar night can last about 14 Earth days. Dust works into seals and joints. It is sharp, clingy, and unpleasantly good at following astronauts indoors. So every local resource comes with a machine attached. Ice needs to be found, dug up, heated, cleaned, and stored. Oxygen in rock must be released through industrial processing. Soil used as shielding has to be moved by equipment that can survive dust, radiation, and extreme temperatures. If power fails, the resources remain exactly where they were, locked in the ground. This is the awkward part of calling the moon a lifeboat. A lifeboat normally arrives stocked, sealed, and ready to float. The moon offers neither the boat nor the supplies. It offers timber, metal, and a nearby shore where people might build one. Proximity makes repair, trade, and emergency support far more practical than they would be on Mars. Local ice and minerals could reduce the mass launched from Earth. Yet neither advantage creates a breathable atmosphere, dependable power, or the factories needed to replace broken systems. So, if the Moon is our easiest backup, how much must Earth still provide before that backup can keep anyone alive? The Moon's gravity is only 1/6 as strong as Earth's, and that changes almost everything a settlement tries to keep alive. A person can learn to walk there, a building can be designed for the lighter pull, but no one knows what years of lunar gravity would do to a human body. Astronauts in orbit lose bone and muscle unless they exercise for hours. The Moon would give their bodies some weight, but far less than the weight we evolved under. Children would present an even harder problem. We have no evidence showing that pregnancy, growth, and lifelong health can proceed normally at 1/6 gravity. A lunar town could shield people from radiation and still leave this basic risk unresolved. The weak gravity also helps gases escape. Earth holds a thick atmosphere because its gravity pulls hard, while its magnetic field and constant geological recycling help maintain the system. The Moon has almost no atmosphere at all. Any breathable air around a settlement must stay behind walls. That sounds manageable until you remember how eagerly gas finds a bad seal. Every hatch, pipe joint, window, and cable opening becomes part of the pressure vessel. A tiny leak may be repairable. Many tiny leaks become a permanent demand for new gases, replacement parts, and skilled work. You're not living beside the environment. You're living inside a machine that must never stop being a machine. Then comes the lunar night. Most places near the equator spend about 14 Earth days in sunlight, followed by about 14 Earth days in darkness. Solar panels work beautifully until the sun drops below the horizon. After that, the settlement needs stored energy or another power source for nearly 2 weeks. Batteries large enough for that job bring their own mass, wear, and replacement cycle. Nuclear systems can provide steady power, but they require fuel, cooling, maintenance, and equipment that a young settlement may not be able to make. Even near the poles, where some high ground receives sunlight for long periods, shadows move and failures still happen. This is why having resources nearby isn't the same as being able to use them. Ice cannot become drinking water, oxygen, and rocket fuel without power. Metal in the soil cannot become a pressure valve without mining machines, furnaces, precision tools, and people who know how to run them. The Moon may shorten the supply line. It does not remove it. And the more a settlement grows, the more its survival depends on an industrial chain built inside a place that offers no air, little gravity, and nights long enough to drain almost any simple plan. The Moon still gives us something no station in orbit can offer. It has ground. It has water ice in some polar shadows. Its soil contains oxygen bound inside minerals, and because it sits close to Earth, a cargo flight takes days rather than months. That closeness changes what people can attempt. Crews could learn to excavate soil, protect shelters, and repair equipment far from immediate help. They could test ways to make oxygen and fuel from local material. A lunar base could also support telescopes, science, and missions farther into space. It would extend our reach in a very practical way. But extending our reach is different from replacing our home. A house near a forest may have plenty of timber. That doesn't mean the forest supplies finished walls, warm rooms, clean water, and electricity. Raw material becomes useful only after a working system collects it, processes it, and delivers it where needed. On the Moon, every part of that system must survive dust, radiation, extreme temperatures, and low gravity. Air is the clearest example. Oxygen in lunar rock isn't waiting in a convenient tank. Machines must crush the rock, heat it, and separate its chemicals. Those machines need steady power. They need cooling, spare parts, and maintenance. If one essential pump stops, the Moon doesn't provide a breeze while someone finds a wrench. Power creates the same problem. Long periods of sunlight near the poles can help solar equipment. They cannot guarantee electricity through every shadow, fault, or dusty surface. Batteries wear out, cables break, reactors need control systems and shielding. A settlement would need several sources of power backed by storage and repair capacity. Then comes industry. Making a rough metal block is one achievement. Making a reliable seal, computer chip, medicine or pressure sensor is another. Earth produces these things through enormous networks of mines, factories, laboratories, trained workers and transport. Rebuilding even a small share of that network on the Moon would take time, mass, and a great deal of energy. So the Moon can make human life beyond Earth more capable. Local water can reduce some cargo. Local oxygen could support breathing and propulsion. Nearby ground gives us room to build and learn, yet Earth remains the source of the atmosphere, power systems, machines, and industrial depth that keep those efforts alive. The Moon could become an outpost with growing independence. But how much of Earth's support would it have to reproduce before a broken supply line stopped being an emergency? Mars looks more generous than the Moon in several practical ways. Its air is unbreathable, its ground is cold, and its surface is flooded with radiation. Yet the planet offers settlers more raw material to work with. A Martian day lasts about 24 hours and 39 minutes. That is close enough to an Earth day for sleep, work, and power use to follow a familiar rhythm. Crews would still need to adjust, but their clocks would not be fighting a completely alien cycle. Gravity is another advantage, though we should be careful with that word. Mars has about 38% of Earth's gravity. A person who weighs 180 pounds on Earth would press down with about 68 pounds there. That makes lifting equipment easier. Dust and loose objects still settle. Liquids still have a clear downward direction. We do not know whether 38% gravity is enough to protect the human body for decades. Astronauts in near weightlessness lose bone and muscle unless they exercise hard. Mars may reduce that damage, or it may only slow it. No human has lived in Martian gravity long enough to tell us. Then there is the atmosphere. It is thin, with less than 1% of Earth's surface pressure, and roughly 95% of it is carbon dioxide. You could not breathe it. You could, however, feed it into machines. In 2021, a small device called MOXIE began working aboard NASA's Perseverance rover. It pulled carbon dioxide from the Martian air and split it, producing oxygen. The amounts were tiny. Still, the chemistry worked on Mars, using material already there. But oxygen could one day support crews or help burn rocket fuel. Carbon dioxide, water ice, and Martian minerals could also become inputs for fuels, plastics, bricks, and other basic products. Mars does not hand settlers a factory. It supplies part of the stockroom. And that changes the scale of the challenge. A settlement able to gather air, water, and building material locally could depend less on cargo from Earth. But every local process adds pumps, filters, seals, heaters, sensors, and software. Each one can fail. Earth would be millions of miles away, or millions of kilometers away. Depending on the planet's positions, a message could take roughly 3 to 22 minutes to travel one way. A spare part would take months. Mars gives people more chemistry to work with, while making rescue slow and repair unavoidable. So which systems would settlers have to make first, before local resources became a real safety net instead of another set of machines waiting to break? Mars offers a strange bargain. Its atmosphere is almost entirely carbon dioxide. People can't breathe it, but each carbon dioxide molecule contains oxygen that a machine can pull free. NASA tested that idea with MOXIE, a small experiment aboard the Perseverance rover. From 2021 to 2023, MOXIE pulled thin Martian air through a filter. It heated the carbon dioxide, split the molecules apart, and produced ordinary molecular oxygen, the same kind we breathe. It worked. Across 16 runs, MOXIE made 122 grams of oxygen. That's about 4 ounces. At its best, it produced 12 grams an hour. That's enough for a small dog to breathe for roughly 1 hour. For a device about the size of a car battery working on Mars, that was a serious result. But a settlement would need far more than a car battery could make. Astronauts would need oxygen to breathe. Their rocket would need much more as an oxidizer, allowing its fuel to burn during the climb from Mars. One proposed ascent vehicle might require about 25 metric tons of oxygen. That's roughly 55,000 pounds, and more than 200,000 times everything Moxie produced. Making it would be only the beginning. The oxygen would have to be cleaned, compressed, and stored safely. It would need to be ready before the crew trusted it as part of their ride home. It's like catching rain in a cup, then being asked to supply a town through summer. The cup proves there's water. It doesn't prove the pumps, tanks, pipes, and treatment plant can work every day for years. A full oxygen plant would need steady power. Its filters would have to survive Martian dust. Hot parts would face thousands of heating cycles. Compressors, valves, and storage tanks couldn't leak, and if a small part failed, nobody could order another and expect it on Tuesday. The settlers would have to find the fault themselves. Then they would need to repair the part, make a replacement, or rebuild the system around whatever still worked. That demands tools, raw material, machine shops, trained people, and enough spare capacity to keep producing oxygen during repairs. Mars provides carbon dioxide, water ice, and useful minerals. It also puts every workshop months from physical help. Local production reduces dependence on Earth, while turning mines, factories, and repair shops into life support systems. Moxie proved that one small machine could make oxygen on Mars. A settlement would have to expand that success into an industry, then keep the whole chain running when something inevitably broke. Mars gives settlers something the Moon cannot offer in the same amount: a planet's supply of carbon dioxide, buried water ice, and mineral-rich rock. And that sounds like freedom from Earth. It could become freedom eventually. But greater distance also makes failure harder to forgive. A broken pump in Antarctica can bring experts onto the radio within seconds. Aircraft may be delayed by weather, but help remains on the same planet. On Mars, even your message takes about 3 to 22 minutes to travel each way. The delay changes as Earth and Mars move around the Sun. By the time advice arrives, the crew may have tried the wrong repair. During a fast-moving emergency, even a good answer could arrive too late. Physical rescue is much slower. Crews cannot leave Earth whenever they please. Good launch opportunities come about once every 26 months. After launch, the trip usually takes several months. If a critical system fails, there is no rescue vehicle waiting nearby. Help may be on another planet, with both planets in the wrong positions. Mars also adds a burden that local mines cannot remove. Its atmosphere is less than 1% as thick as Earth's. It has no strong global magnetic field. This leaves the surface exposed to more radiation from space. Since 2012, NASA's Curiosity rover has measured that radiation inside Gale crater. The amount changes, but the conclusion does not. People living there would need shielding. The ground could provide some protection. Martian soil piled over a habitat can absorb radiation. Water stored around sleeping areas can help too. But we still have to dig, move, and support all that weight. The machines need power, parts, and maintenance. Protection becomes another system that can fail. A damaged rover or excavator could delay work on the very shelter, keeping everyone safe. That is the awkward trade Mars offers. It has more raw material for building an independent settlement, while placing that settlement beyond quick rescue. Making more things locally reduces deliveries from Earth. Yet every mine, reactor, greenhouse, and workshop creates another place where a small fault can spread. A backup world would need enough people and equipment to repair several failures at once. It would need stored food, air, water, and power, while those repairs took longer than planned. Earth could advise. It might send replacements during the next launch window, but nobody on Earth could reach across space and turn a wrench. So how large would a Mars settlement have to become before distance stopped turning every serious failure into an emergency? Most of us would judge a settlement's safety by its oxygen gauge. If the air is still breathable, the machines must be doing their job. That makes sense for the next few minutes. Over years, though, oxygen may not be the hardest thing to replace. A well-equipped settlement could split water into hydrogen and oxygen, plants could help recycle carbon dioxide, Stored tanks could cover short interruptions. None of that makes air simple. It does mean the obvious emergency isn't always the deepest one. Think about an old house. The building may have plenty of electricity, yet one failed rubber seal can leave water spreading across the floor. The costly system is stopped by a part small enough to lose in a kitchen drawer. A space settlement would contain thousands of those parts. Seals around hatches, valves, pumps, toilets, pipes, and pressure suits would flex and age. Lubricants could dry out, filters would clog, bearings would wear, some metals would become brittle. A machine might remain mostly intact, while one tiny surface no longer closes properly. Keeping spares sounds easy until you ask which spares. Store too few, and an obscure failure can stop a vital machine. Store everything, and the settlement becomes a warehouse with a rocket problem. Parts also have shelf lives. Rubber changes with age. Electronics can suffer radiation damage. Batteries lose capacity. A replacement kept for 10 years may fail when someone finally opens its package. Then there are catalysts. These are materials that help chemical reactions happen without being used up in the usual way. They might help clean air, process fuel, make fertilizer, or turn local material into something usable. But catalysts can be damaged by heat or poisoned by trace chemicals. A speck of the wrong substance can coat the working surface. The catalyst is still there. It simply stops doing its job. Sensors create another awkward weakness. You can't manage air, water, pressure, heat, or radiation if the measurements drift. A sensor may keep producing a number after it becomes inaccurate. That's worse than a blank screen, because the settlement may trust it. Crews would need reference instruments, calibration materials, and ways to compare several readings before acting. Contamination can spread through all of this. On Earth, a workshop can open its doors, replace a dirty pipe, or order a new batch of chemicals. A sealed habitat has fewer exits. Metal dust from machining can enter electronics. Microbes can grow in damp plumbing. Oils can coat filters. One careless mixture can spoil material intended for farming or manufacturing. Cleaning is therefore part of production. So is testing. So is keeping dirty work away from clean work. The settlement needs gloves, solvents, sterile containers, sampling kits, and people trained to notice a small change before it reaches the air loop or the food supply. This changes what self-sufficiency means. Making oxygen is impressive, but it doesn't prove the oxygen system can be maintained. Making a metal bracket doesn't prove the settlement can produce its coating, inspect it for cracks, or manufacture the seal fitted beside it. Local industry must reproduce chains of small abilities, not just a few large machines. And those chains can fail in ordinary ways. The right spare exists, but its storage record is wrong. The sensor works, but nobody has a trusted standard for checking it. The chemical plant runs, but an impurity slowly ruins its catalyst. No single event looks dramatic. Then several systems begin giving trouble at once. So the most revealing gauge may not show oxygen, water, or power. It may show how many kinds of failure the settlement can diagnose and repair without opening a shipment from Earth. How do you measure that before lives depend on it? Most of us would put breathable air at the top of any settlement's survival list. Yet the machine making that air may be stopped by a rubber ring small enough to hide in your palm. That ring is a seal. It sits between two surfaces and stops gas or liquid from escaping. Seals age. Heat makes them brittle. Radiation can change them. Dust scratches them. While chemicals make some swell or soften, a habitat may have plenty of oxygen stored away and still lose the equipment needed to move, clean, or measure it. This is why spare parts can outrank raw supplies over the long run. A tank of oxygen solves one shortage. A box of the right seals may protect a dozen systems. Pumps need them. Airlocks need them. Water pipes need them. Chemical reactors need them. The settlement doesn't survive because it owns many objects. It survives because it can keep those objects working. The awkward part is that a spare isn't merely a shape. It also has to be the right material. A replacement that fits perfectly might react with the fluid touching it. It might crack in the cold or release gas into clean air. On Earth, that mistake usually becomes a delayed repair and an annoyed purchasing department. Far from Earth, it can disable the backup beside the original failure. Catalysts create a similar problem. A catalyst helps a chemical reaction happen without being consumed in the usual way. You can think of it as a good kitchen surface. The ingredients change, while the counter remains ready for the next batch. But a little contamination can cover that working surface. The catalyst is still present, it just can't do its job. That can affect systems that clean water, process waste, make fuel, or remove unwanted gases. The feedstock may be abundant. The reactor may have power. Every large component may look fine. A trace impurity, too small to notice without careful testing, can still slow the whole process until its output becomes unusable. Sensors are another fragile link. A habitat depends on devices that detect pressure, temperature, moisture, toxins, and tiny changes in chemical mixtures. But sensors drift. Their readings slowly move away from reality. If there's no reliable way to check them, the crew can end up maintaining the number on a screen instead of the system behind it. You know this problem from an unreliable bathroom scale. If it adds 2 pounds each week, your weight hasn't necessarily changed. The instrument has. Now replace body weight with carbon dioxide, reactor pressure, or contamination in drinking water. A small error can send people toward the wrong repair, while the actual fault keeps growing. Contamination control ties all of these problems together. Dust, skin oils, metal flakes, microbes, and chemical residue travel on hands, tools, clothing, and airflow. One careless repair can spread trouble from a workshop into equipment that was working well. Cleaning is therefore part of manufacturing. So are sealed storage, verified procedures, and records showing which material touched which surface. A mature settlement will need shelves of ordinary parts, ways to test them, and processes clean enough to trust the result. It will need fresh catalysts or methods for restoring them. It will need reference standards for its sensors. It will need people who can spot contamination before contamination becomes a system-wide fault. Oxygen is essential, of course, but oxygen is visible in the plan, measured in tanks and daily consumption. The first irreplaceable thing may be less impressive: a seal with the correct chemistry, a clean catalyst bed, or a sensor that still tells the truth. We often call a habitat closed when it recycles something important. Water runs through a filter. Air passes through scrubbers. Yesterday's waste becomes tomorrow's raw material. It sounds complete, but a loop can circle many times while still depending on Earth to keep it moving. An open-loop system is the simplest case. Supplies arrive, people use them, and the waste leaves or piles up. A camping trip works this way. You carry food, fuel, batteries, and clean water. When they're gone, the trip ends unless someone brings more. A partial loop sends some material around again. Think of a kitchen jar filled from a large water container. You can wash that jar and use it every day. The jar has a loop. The water supply does not. Once the container is empty, washing the jar won't fill it. Most space life support systems combine many partial loops. Water can be recovered from breath, sweat, and urine. Carbon dioxide can be removed from cabin air. Some oxygen can be produced again. Each step reduces the supplies that must arrive from Earth. That's a major gain. It allows longer missions and cuts the mass carried on each flight. But making a delivery last longer is different from no longer needing one. Filters wear out. Chemicals become contaminated. Crops need nutrients in forms their roots can absorb. Machines lose small amounts of gas and water through leaks, cleaning, sampling, and repairs. People still need calories, medicines, clothing, electronics, and replacement materials. So a habitat might recover 90% of its water and still rely on cargo. The missing 10% is only part of the problem. The pumps need seals, the sensors need calibration. The treatment system may need fresh chemicals and parts made from materials the habitat cannot produce. The water travels in a circle, while the machinery supporting that circle sits at the end of a supply line. A truly closed system has a much harder job. It must recover what people use and return it in a safe form. Then it must replace what the recovery process consumes. It also needs stored material to cover losses that cannot be reversed. Nothing people build will be perfectly closed. Some gas escapes. Some material becomes too mixed or contaminated to recover. The practical target is less absolute. Losses must become small enough and local replacement broad enough that survival no longer depends on frequent cargo from Earth. A resupply could still arrive. It might bring rare medicines, new equipment, or a few comforts from home. It just wouldn't stand between the settlement and a slow failure. Scale changes the answer as well. A crew of 6 can live for months with carefully packed spares. A settlement of 6,000 cannot treat every broken pump, failed light, missing nutrient, and medical shortage as a special shipment. More people provide more skills and labor. They also create thousands of daily material flows, each with its own losses. This is why closure is not one percentage. A habitat might close its water loop while leaving its food loop open. It might grow food while importing fertilizer. It might recycle metals while importing the tools that do the recycling. Even a high recycling rate can hide one small imported part that the whole system cannot run without. That is the awkward difference between surviving longer and becoming a settlement. Recycling can stretch the clock for years. Settlement begins when local systems can replace the things that keep that clock running. The dividing line is whether people can replace what recycling consumes at the scale where they intend to stay. And if every loop closes by a different amount, which one has to close first? Water seems like the obvious loop to close first. People need it every day. It is heavy to carry, and most of it can be cleaned and used again. But a settlement can recover nearly all its water and still depend on Earth for the parts that make recovery possible. A filter does not last forever. Neither does a pump seal, a valve, a sensor, or the chemical bed that pulls waste from the stream. Keeping those parts on a shelf buys time. Sending replacements every few years buys more. Neither arrangement lets the settlement replace what wears out. This gives us a sharper dividing line. Extended survival means supplies arrive less often. A replacement civilization can produce the supplies, machines, and knowledge needed to keep its essential systems alive. That is a much taller order than recycling water or air. Think about a simple kitchen tap. It looks like one object. Behind it sit pipes, seals, metal fittings, treatment plants, electric motors, control boards, mines, factories, and trained workers. A habitat tap carries an even longer chain, because failure may leave no nearby backup. Food has the same hidden depth. Growing lettuce under lamps proves that plants can grow away from Earth. It does not prove that a community can replace its entire food system. The lamps age, nutrients leave with waste or become trapped in forms crops cannot use. Diseases spread through closely managed plants. Seeds must remain healthy across generations. The growing room also depends on fans, cables, cooling equipment, and software. You can stretch each of those systems with careful recycling. You can carry spare lamps, extra seed, and several years of fertilizer. That may turn a 6-month mission into a long residence. It still leaves Earth sitting invisibly inside the walls, packed into every item that cannot be made locally. Settlement scale makes this harder. One damaged pump may be manageable for 20 people. The same weak point, repeated across a city, becomes a steady demand for materials and labor. More residents also need more farms, more power, more medical care, and more equipment for making equipment. The system grows wider, but its supply chain must grow deeper too. So the threshold cannot be measured only by how long people survive between cargo ships. A century of stored parts would be an extraordinary engineering achievement. Yet, if the final essential part still has to come from Earth, the settlement remains attached to Earth by a very long cord. Crossing the threshold means being able to replace that part without help. People must find the raw material, refine it, shape it accurately, test it, install it, and teach the next generation how to repeat the work. They also need enough spare capacity to recover from mistakes A workshop that can make one perfect valve under ideal conditions is different from an industrial system that can supply thousands while repairing its own machines. Complete independence may never be practical or desirable. Cities on Earth trade because trade is efficient. They do not each mine every metal or build every computer. A space settlement could trade too. The distinction is whether trade improves life, or whether one missed shipment begins a countdown. That is why longer is not the same as forever. Resupply can become rare. Recycling can become remarkably good. Stored equipment can last for decades. But a replacement civilization begins only when the people who stay can rebuild the systems that let them stay. And that leaves the first real test. Which imported part would start the countdown soonest? A settlement can keep its machines running and still ask too much of the people inside it. Human bones, unlike pipes and pressure seals, rebuild themselves according to how hard gravity makes them work. On Earth, every walk to the kitchen gives your skeleton a small job. Your legs carry your weight, muscles pull against bone. Each step tells living bone tissue that the structure is still needed. Remove that daily load and the body starts saving material. Astronauts in orbit can lose bone from weight-bearing areas much faster than adults usually do on Earth. NASA has measured average losses of around 1 to 1.5% per month in parts of the hip and spine during long missions. That's roughly the kind of change that might take a year in an older adult on Earth, compressed into a month. The body isn't failing at random. It's adjusting to a place where heavy bones cost energy, but no longer help you stand. Calcium released from bone enters the blood and urine. That can raise the risk of kidney stones during a mission. Later, when an astronaut returns to full gravity, weaker bones must suddenly carry full weight again. So crews exercise a lot. On the International Space Station, astronauts commonly spend about 2 hours each day on exercise and related setup. They run while straps hold them to a treadmill. They pedal a stationary bicycle. They use a resistance machine that imitates heavy lifting without ordinary weights. A loose barbell in orbit would simply float beside you, which makes the usual gym routine slightly impractical. These countermeasures help. Modern resistance training has reduced bone loss compared with earlier missions. Good food and enough vitamin D support the same effort. Some astronauts preserve bone better than others, which shows how much individual response can vary. But exercise doesn't recreate a normal day on Earth. It gives the body a planned dose of loading, then leaves the crew weightless for most of the remaining hours. Orbit is also only one case. The Moon has about 1/6 of Earth's gravity. Mars has a little more than 1/3. Those numbers sound reassuring because neither place is weightless. Yet no human has lived for years under either level. Apollo crews spent only days on the lunar surface. We don't know whether lunar gravity can maintain healthy bones across decades, or whether Martian gravity crosses some protective threshold. Adults are the easiest group to discuss because their skeletons have already formed. Pregnancy and childhood raise harder problems. A fetus builds bone while floating in fluid, but the mother's body is still developed under Earth gravity. After birth, gravity helps shape movement, muscle, balance, and the growing skeleton. It may also affect systems beyond bone in ways that short adult missions cannot reveal. No human pregnancy has occurred on the Moon or Mars. No child has grown there. Animal studies can show possible effects, but they cannot give us a safe minimum gravity for a human childhood. They also cannot tell us whether problems would appear at birth, during puberty, or much later in adult life. That leaves a difference between survival and settlement. A trained adult crew might live and work for years with strict exercise, medical checks, medication, and eventual treatment on Earth. A permanent population cannot assume everyone is a screened astronaut. It includes injuries, aging, pregnancy, infancy, and people whose bodies do not respond to exercise in the same way. Rotating habitats could create artificial gravity, though building them adds size, motion, and engineering demands. Without them, a colony would be running a long biological experiment with every generation included. Keeping adults alive and working would be an achievement. It still wouldn't prove that pregnancies can remain healthy or that children can grow into healthy adults there. So before we call a place a second home, how much gravity does a human life actually need? Keeping a crew alive for several years can look like proof that a settlement works. But survival is only the first biological test, and perhaps the easiest one to recognize. Adult astronauts arrive with bodies that finished growing on Earth. Their bones, organs, immune systems, and reproductive systems developed under Earth's gravity. They are carefully selected, closely watched, and trained to notice small changes. If something begins to go wrong, doctors can compare new readings with years of medical records. They can also send treatment, change the mission, or bring the astronaut home. A child gets no such starting point. Every part of the body must assemble itself in the new environment. Cells divide, organs take shape, bones lengthen, the brain builds connections at extraordinary speed. Gravity and radiation act throughout that process. They aren't added after the work is done. Radiation is especially awkward because damage can remain hidden. A bad burn announces itself. A changed cell may not. High-energy particles can pass through tissue and damage DNA, leaving the body to repair the break. Most repairs succeed, some don't. The consequences may appear years later, after the original exposure has been forgotten. For an adult crew, that risk can be managed within a limited mission. Exposure can be measured. Shelters can protect people during solar storms. Doctors can watch for cancer, changes in the eyes, or damage to the nervous system. A settlement has a longer clock. It asks what repeated exposure does across an entire lifetime, then across several lifetimes. It must also account for people who were never screened for unusual physical resilience. Reproduction raises the standard again. An embryo begins as a small number of rapidly dividing cells. A mistake in one early cell can be copied into many later cells. On Earth, pregnancy already depends on careful timing, blood flow, hormones, nutrition, and normal development of the placenta. Away from Earth, lower gravity and higher radiation would enter that process together. Shielding might reduce one risk while leaving the other almost untouched. We don't yet have human evidence that settles this. No person has been conceived, carried through pregnancy, born and raised beyond Earth. Animal studies can reveal warning signs, but they cannot tell us exactly how a human pregnancy would unfold. Different species develop at different speeds. A mouse is not a small human with whiskers, convenient though that would be. Even a healthy birth would only begin the test. A child's skeleton responds to weight and movement as it grows. Muscles learn what loads to expect. Balance develops from signals shared among the eyes, inner ears, brain, and limbs. Lower gravity could alter that development in ways an adult exercise program cannot reverse. A treadmill may help maintain an adult's bones. It cannot replay childhood under different physical conditions. Then comes puberty. Reproductive cells must remain healthy. Hormone systems must mature normally. The first generation must be able to produce a healthy second generation. Those children, in turn, must grow and reproduce without damage building up each time. Otherwise, the settlement is not a lasting population. It is a remote workplace that depends on regular arrivals from Earth. This difference can hide behind impressive numbers. A base might report enough food, enough oxygen, and years without a fatal accident. Its adults might work, exercise, celebrate birthdays, and grow old there. All of that would count. None of it would show that the place can carry human life safely through every stage. A viable society needs bodies that can begin there, develop there, and remain healthy without Earth serving as the medical exit door. Keeping adults useful for years proves endurance. It does not prove inheritance, pregnancy, childhood, or another healthy generation. So what evidence would be enough before anyone asks the first children born there to carry that risk? Most plans for feeding a settlement begin with a greenhouse, and the greenhouse usually looks reassuring. Rows of lettuce glow beneath lamps. Clean roots hang in water. Every green leaf seems to say that dinner has been solved. Lettuce can grow this way. So can herbs, tomatoes, and several other crops. Hydroponics gives roots water and dissolved minerals without soil. It can save water, limit pests, and produce fresh food in a small area. For a remote outpost, that would be valuable. But fresh leaves are not a food system. You can eat a large bowl of lettuce and still be short of energy. Settlers need carbohydrates, fats, and proteins in dependable amounts. They need fiber, vitamins, minerals, and enough variety to keep eating well for years. That leads away from the display greenhouse and toward wheat, potatoes, soybeans, beans, and oil-rich seeds. Those crops need space, light, labor, processing equipment, and time. Then there is everything beneath the menu. On Earth, a farm borrows services from an entire living world. Bacteria make nutrients available. Fungi work around roots. Insects pollinate many plants. Other organisms break dead material apart. Soil, weather, and groundwater absorb mistakes that a farmer may never notice. Inside a settlement, those jobs still have to happen. Machines and chemicals can replace some of them. Carefully managed microbes or insects may do others. Either way, the settlers are no longer tending crops alone. They are operating a small ecology with plumbing attached. That ecology can fail in very ordinary ways. A pump stops. Fungus reaches the roots. A pollinator colony dies. A nutrient mixture contains too much of one mineral and too little of another. A crop carries a virus before anyone sees marks on its leaves. On Earth, a failed greenhouse can buy food from somewhere else. Far from Earth, the failure arrives at the table. Reliability changes the whole design. You need spare pumps, stored seed, backup lighting, protected water, and more than one source of essential calories. Separate growing rooms may stop one disease from reaching every crop. You also need food reserves, because plants don't hurry when a machine breaks. Wheat planted today cannot become emergency bread tomorrow. People add another complication. They don't eat nutrient charts, they eat meals. Flour must become bread or noodles. Soybeans need preparation. Potatoes need storage. Oils must be extracted. That requires kitchens, mills, storage rooms, refrigeration, and people who know how to use them. Tough stems, roots, spoiled produce, and kitchen scraps also need handling. Some material can go back into crop production. Some may carry salt, pathogens, or chemical residues that make reuse unsafe. Diets change too. A child needs something different from a working adult. Illness can change what someone can digest. Pregnancy raises certain nutritional demands. Age can change appetite, chewing, and nutrient needs. A settlement built around one efficient menu may discover that its efficiency was measured for the wrong bodies. And even a complete diet on paper may become unbearable if every week tastes the same. And that is why a few successful harvests prove less than they seem. They show that plants can grow. They don't show that hundreds of people can be fed through equipment failures, crop disease, changing health needs, and bad harvests that arrive close together. A food system has to survive its worst season, not merely photograph well during its best one. So how much growing space, machinery, stored food, and biological backup would keep a settlement fed when the greenhouse has a bad year? A greenhouse makes farming on Mars look almost familiar. There are leaves, lamps, pipes, and perhaps one tired person arguing with a tomato plant. But a settlement can't live on the fact that plants grow there. Food must keep arriving when several ordinary problems happen at once. That changes the farming problem. Raising one healthy crop under controlled conditions isn't enough. You need a small ecology that feeds people every day without help from Earth. Crops share light, water, nutrients, space, labor, and machines. They must also fail in different ways, so one accident can't empty every plate. Farms on Earth depend on an enormous living network. Soil contains fungi, bacteria, insects, minerals, and decaying matter. Rain and rivers move water. The atmosphere softens temperature changes. Seeds, fertilizer, fuel, spare parts, and replacement machines can come from elsewhere. A farmer can call a mechanic. A settlement on Mars would carry much of that support inside its walls. Even a salad depends on hidden partners. Microbes around plant roots help release nutrients. Those microbes need suitable moisture, temperature, and chemistry. If conditions shift, Helpful organisms may struggle while disease spreads through crowded crops. Shared air and water save resources, but they can also carry trouble from one growing bed to another. That makes diversity part of the equipment. Wheat can supply calories, beans can provide protein, potatoes can produce plenty of food in limited space, fruits and leafy crops add nutrients that stored staples may lose over time. Yet each crop wants different conditions. Some take months to mature, some need pollination, some leave stems, roots and husks that people can't eat but still must handle. This farm would feel more like a ship's engine room than a garden. Pumps move water, fans control heat and moisture, sensors watch the air and roots, lamps provide light during dust storms or inside buried rooms. If one pump stops, the crew needs another. If fungus reaches one room, sealed sections may protect the others. Seeds matter, but so do valves and wiring. And crop failures move slowly. A broken air filter becomes urgent within minutes. A lost harvest may take weeks to show its full cost. By the time leaves wilt, the following crop may already be damaged. Stored grain and frozen food can cover the delay, but every reserve requires mass, power, cooling, sealed containers, and protected space. Deliveries from Earth add protection, though they can't be the foundation. Earth and Mars orbit the Sun at different speeds. The easiest launch opportunities return about every 26 months. That's a little over 2 years. A missed shipment can't leave the following Tuesday. Bad weather, a launch failure, or trouble in transit could make the wait much longer. Food autonomy doesn't mean growing every meal from the first day. It means reaching a point where delayed cargo is inconvenient rather than deadly. We would need spare machines, separated crop rooms, stored calories, seed reserves, trained growers, and enough variety to stop one disease from becoming a famine. There's also the person arguing with a tomato plant. That person must repair the habitat, care for patients, do other work, and occasionally sleep. A farm that survives only through constant expert attention isn't reliable. It has turned hunger into a full-time emergency. The first farmers on Mars would manage an ecology under pressure, with no nearby countryside to absorb a mistake. So how large and complicated must that ecology become before it can feed a town without waiting for Earth? A broken metal bracket seems like a small problem until it holds the only working pump in town. On Mars, that little piece may be months away from the nearest warehouse. This is where local fabrication earns its place. A workshop could measure the broken part, adjust a digital design, and make a replacement nearby. A metal printer might build it layer by layer. A milling machine might cut it from a block. Either route could turn raw stock into a working shape without waiting for a rocket. That would be a serious improvement. Space crews already use versions of this idea. In 2014, a printer aboard the International Space Station made the first object manufactured away from Earth. It was a small plastic part, more demonstration than rescue. Later experiments printed tools, test pieces, and simple components. The lesson was modest but real. Some objects can be made where they're needed. You can see why this sounds like the beginning of independence. Send the printer once, then send designs instead of boxes. A missing wrench becomes a file. A cracked cover becomes an afternoon in the workshop. Shelves can hold feedstock rather than every possible spare part. But a printer doesn't create material. It rearranges material already prepared for it. Plastic filament has to be chemically suitable, clean and consistent. Metal powder needs the right alloy, grain size and purity. A machine designed for stainless steel can't be handed a scoop of Martian dust and asked to improvise. Even the bracket hides a long chain of work. Someone has to find useful ore, separate it from unwanted rock, remove oxygen or other bound elements, refine the metal, mix the alloy, and form it into powder, wire, or a solid block. Each step needs equipment. That equipment has bearings, seals, motors, sensors, cables, and control boards of its own. Then there's accuracy. A bracket that merely resembles the old one may still fail. Its holes must line up. Its metal must handle the load. It may need heat treatment so it doesn't crack. If it sits inside an oxygen system, its surface and composition can't introduce a fire risk. Making the shape is only part of making the part. A settlement could test its work with gauges, scanners, and load machines. It could keep proven designs and record which batches of material performed well. That begins to look less like one miraculous printer and more like a compact factory, with inspection, maintenance, and people who understand why a component failed. Some items would remain much harder. A rubber seal depends on precise chemistry. A camera sensor needs exceptionally pure material and microscopic structures. A modern computer chip is built through hundreds of controlled operations in facilities cleaner than an operating room. You don't print one beside the broken pump. So local workshops could remove many urgent weaknesses without reproducing every industry on Earth. They could make ducts, housings, pipes, furniture, tools, brackets, and plenty of rough mechanical parts. They could repair machines by combining newly made pieces with stored motors, electronics, and specialty seals. That mixed approach might support a settlement for years. It still leaves a slow problem. Stored advanced parts get used up. Machines wear down. Dust reaches almost every exposed surface. Eventually, the workshop needs parts that its own workshop cannot make. A durable settlement would have to keep pushing downward through the manufacturing chain. First shapes, then dependable materials, then precision components, then the machines that produce those components. How far down must that chain reach before Mars has an industry rather than a workshop living from a very large box of spares? A factory can look complete while depending on half the planet. Its machines may sit under one roof, yet the materials, tools, and measuring devices inside them come from thousands of other places. Take a simple electric motor. Mars might cast its metal housing and machine its shaft, but the copper wire needs insulation that survives heat without cracking. The bearings need steel with a controlled mix of elements. Their surfaces must be ground smooth within tiny limits. Magnets may require rare earth metals, careful heating, and protection from corrosion. Then come lubricants, adhesives, sensors, connectors, and electronic controls. Each item has its own family tree. Even a bolt carries more history than its shape suggests. Ore had to be mined, separated, and refined. Carbon and other elements were added in measured amounts. The steel was heated, rolled, cut, hardened, and tested. The cutting tool that formed the threads was made from another special alloy. The gauge that checked those threads came from a precision workshop. Its measuring equipment was checked against another trusted standard. A printer can copy the bolt's outline. It cannot automatically copy that entire chain. Nor can a machine shop judge every hidden flaw just by looking at the finished part. Electronics reach much farther down. A computer chip begins with silicon that must be made extremely pure. It is formed into a crystal, sliced into thin wafers, polished, coated, exposed to patterned light, etched, and treated with tiny amounts of other elements. Many of those steps happen in rooms with fewer airborne particles than a hospital operating room. A speck of dust too small for you to see can ruin part of the wafer. Those rooms need filters, pumps, gases, solvents, masks, lamps, robots, and inspection systems. The inspection systems contain their own chips. The pumps have seals and bearings. The lamps depend on carefully made glass and stable power supplies. Manufacturing starts to fold back on itself. Advanced factories need products from other advanced factories before they can make anything at all. Medicine adds another layer. A settlement may know the formula for an antibiotic or a hormone. That doesn't mean it can safely make one. The process needs controlled biological cultures or chemical reactions. It also needs pure ingredients, sterile vessels, clean water, and tests that can detect contamination. A batch can look normal and still contain the wrong dose or a harmful byproduct. Knowing the recipe is not the same as owning the kitchen, the laboratory, and every test that says the result is safe. Quality control is part of the product. You don't merely make an oxygen valve. You prove that it opens at the right pressure and closes without leaking. You prove that it keeps doing both after heat, cold, dust, and thousands of cycles. That proof takes calibrated instruments. Those instruments drift with age, so they must be checked against trusted references. The reference itself must remain stable. Earth hides these layers because they usually work. You order a replacement sensor and a package appears. Behind it may sit a mine in one country and a chemical plant in another. There may be a chip factory across an ocean and a testing laboratory somewhere else again. Mars would feel every missing link. A settlement could carry years of spare electronics and medicines. It could design machines around common parts, reuse components, and choose older technologies that are easier to repair. It could standardize bolts, motors, valves, and connectors, so fewer machines need unique replacements. Those choices buy time. They also trade efficiency for independence, which may be exactly the right bargain. But stored supplies still end. Simplified machines still depend on materials made to known standards. So the problem is no longer whether Mars can build a factory. It is how much of Earth's hidden web that factory must rebuild before the next broken sensor becomes an emergency. A Mars settlement could solve that factory problem and still fail as a backup for humanity. Keeping a group of adults alive is one task. Keeping a human population alive across generations is much harder. A research station can work with whoever arrives. A lasting population cannot. It needs enough people of different ages, enough genetic diversity, and enough healthy births to avoid a slow decline that no machine can repair. This is easy to miss because the first crew would be chosen with unusual care. They would be healthy, trained, and screened before leaving Earth. For a while, their survival might look like proof that the settlement works. The harder test begins with people who were never selected on Earth. Children conceived on Mars, children born there, children growing inside lower gravity, breathing recycled air, and eating from a food system with no easy replacement. Mars has about 38% of Earth's surface gravity. We know adults can tolerate months in weightlessness, though their bones and muscles weaken. We don't know whether partial gravity is enough for a pregnancy, a developing brain, or a growing skeleton. No human has been conceived or born beyond Earth. No child has spent the first years of life in reduced gravity. Mice, fish, insects, and plants have reproduced in space experiments. But those results cannot tell us what happens during a human pregnancy. The biology is too different, and most experiments have been small or brief. Even if births were healthy, the population could still drift toward failure. A settlement of 200 people is not simply 200 chances to continue. Ages must line up. Fertility changes over time. Some people will not want children, some will be unable to have them. Others may die before the population can replace itself. On Earth, a small town can absorb a bad decade. People arrive, doctors travel in, frozen embryos can be delivered, a rare genetic disease can be treated by a specialist across the country. Mars would have no neighboring town and no fresh population arriving by road. That makes demographic trouble feel less like a sudden disaster and more like a household budget slipping out of balance. One missed payment is manageable. Then another follows. By the time the pattern is clear, the choices have narrowed. A few difficult pregnancies could change the age structure for decades. A shortage of children today becomes a shortage of workers later. Then fewer young adults means fewer caregivers for an aging population. The settlement may still have lights, crops, and working machines, while its future is already shrinking. Genetic diversity adds another limit. When close relatives have children across many generations, harmful recessive genes are more likely to meet. Stored sperm, eggs, or embryos could widen the genetic pool, yet storage systems fail. Freezers need power, and someone must decide how that material is used. A technical safeguard soon becomes a medical, legal, and deeply personal institution. Researchers can estimate a minimum population with computer models, but the answers vary widely. The result depends on birth rates, death rates, age balance, stored genetic material, accident risk, and how much control the settlement accepts over reproduction. Change those assumptions, and the required population changes with them. So a base can endure for years without proving that humanity could continue there. The first generation might be brave, capable, and comfortable. The second generation would show whether Mars is a home rather than a long mission. And if we cannot test that safely on Earth or in orbit, how would anyone know when a settlement was truly ready? A settlement can have warm rooms, full cupboards, and working machines, yet still be disappearing. The signs may not show up in any daily report. People are alive, crops are growing, children are being born, but the age balance could already be moving in a direction that cannot last. You can see a smaller version in an isolated town. If most young adults leave, the town does not vanish that year. Shops remain open, lights come on, the older residents carry on. Then there are fewer parents, fewer children, and too few workers to replace the people who retire. The town survives each day while losing its future. A Mars settlement could face the same problem, with no neighboring town to help. A few missed births might leave too few people in one age group. An illness could affect several pregnancies at once. A life support accident could take workers who share the same rare skill. Decades later, the settlement may have too few engineers, surgeons, or experienced teachers to train replacements. That delay makes demographic failure hard to recognize. A broken pump gives you an alarm. A population problem may look like ordinary variation for years. By the time the pattern is clear, the people needed to correct it may never have been born. Genetics adds another limit. A small group carries only part of the genetic variation found across humanity. Stored eggs, sperm, and embryos could widen that pool. But storage is not the same as use. Samples must survive launch, radiation, equipment failures, and decades of maintenance. Future doctors would also need the tools and training to use them safely. A freezer full of genetic material is helpful only while the freezer, records, clinic, and medical knowledge all survive together. Then there is the awkward part. Populations are made of people, not numbers in a planning model. A model can assign births to certain years. It can balance ages and limit close genetic relationships. Real people fall in love, refuse treatment, change their minds, lose pregnancies, or decide they do not want children. Any plan that depends on exact reproductive behavior may require rules no free community would accept. Skills behave much like genes. It is not enough to carry a manual for every machine. Someone must understand the system well enough to notice when the manual no longer fits. That knowledge passes through practice. A young technician watches an older one hear a faint change in a motor and recognize trouble before a sensor does. If one generation becomes too small or too busy, that chain can break. Automation can cover some gaps. Machines can monitor crops, diagnose common illnesses, and guide repairs. But automation also creates another skill burden. Someone must maintain the hardware, check the software, and decide when its answer is wrong. A settlement that relies on complex tools needs people who can rebuild those tools after the original experts are gone. This changes what resilience means. It is not merely keeping today's crew alive. It is keeping enough ages, relationships, knowledge, and choices in motion for people who will be born long after the landing. The settlement must absorb bad years without forcing every later generation into a narrower life. And no short mission can prove that. 10 successful years may show that equipment works and adults can adapt. It cannot show that children will grow into healthy parents, that rare skills will keep passing forward, or that a small society can remain stable without harsh control. Those answers arrive slowly, one generation at a time. So before anyone calls Mars a backup for humanity, what evidence would show that its population could still choose its own future? For people already living beyond Earth, the first months after a disaster would be less like founding a new civilization and more like surviving a long power cut. The difference is that nobody can drive over with spare batteries. A crew on the Moon or Mars might have food, water, oxygen, and shelter for months. Some supplies could last longer. Plants might add fresh food and recycle part of the air. Machines could recover water from breath, sweat, and waste. But every loop would leak a little. Filters wear out, pumps fail, crops get sick, stored chemicals run low. Distance would decide how much help remained possible. A lunar base sits about 239,000 miles from Earth, or 384,000 kilometers. If launch sites and spacecraft still worked, people might reach it in days. Mars is different. Depending on where the planets are, the trip is tens or hundreds of millions of miles. A normal transfer takes months, and the right launch window comes roughly every 26 months. So an off-world crew could be alive while rescue was impossible. That isn't the same as being self-sufficient. It means their supplies have not run out yet. This is where both popular endings become too large. A settlement would not automatically die the moment Earth stopped answering. Nor would survival prove that humans had created an independent second home. The people there might keep going for months, perhaps longer, by rationing supplies and repairing whatever they could. Their lives would depend on the exact damage, the equipment already present, and the skills inside the habitat. That scale correction gives us the strongest close available. Space settlements may become valuable refuges, laboratories, and homes. They could save particular people from particular disasters. But a small group surviving away from Earth is a long way from preserving human freedom, health, and choice across generations. If Earth went silent tonight, who could remain alive until the next launch window? And what would still be waiting when it opened? Give that outpost years of warning, though, and the answer changes. Cargo ships could arrive before the emergency, carrying spare parts, medicines, seeds, machine tools, and tanks of stored fuel. Crews could practice losing contact with Earth. They could learn which failures are annoying, which are deadly, and which can be repaired with local materials. A prepared settlement might also make some of its own essentials. Solar panels could supply power. Ice could become drinking water, oxygen, and rocket fuel. Sheltered farms might provide part of the diet. Machines could shape simple replacement parts from metal or rock. None of this makes survival certain. It does move the outpost beyond a campsite with a very expensive supply line. Given enough time, several settlements could support one another. One might have better power systems, another might have deeper stores of food, a third might hold equipment for making medicines or electronic parts. That kind of planning removes some single points of failure. It also gives people options when one habitat has a bad year. So yes, preparation could turn months into years. It might even allow a population to continue through a disaster that ended organized life on Earth. We shouldn't dismiss that possibility simply because the first bases will be fragile. Human beings are remarkably good at making difficult places livable once they have time, tools, and a reason to stay. But the scale still needs correcting. A settlement can survive while remaining poor in choices. Its people may have air and food, yet lack enough doctors, genetic diversity, industrial equipment, or working parts to build a stable society. They may preserve lives without preserving the broad human world those lives once belonged to. That is the stronger case for an outpost, and also its limit. It needn't become a complete copy of Earth to be worth building. It could protect a small branch of humanity when everything nearby has failed. The remaining question is how large, capable, and connected that branch must become before survival stops being temporary. A settlement might last for years and still depend on a supply chain it can't replace. That sounds less like a second Earth and more like a ship whose voyage has no scheduled end. Food is one example. A greenhouse can grow calories, but people need more than calories. They need varied crops, reliable seed, healthy soil or nutrient systems, and backups when fungus, insects, or equipment ruin a harvest. A closed settlement can't simply buy dinner from somewhere else after a bad season. Then there's industry. Making a broken part may require a machine whose own parts came from another machine. Metals must be mined, refined, shaped, and tested. Plastics, glass, electronics, medicines, and fertilizers each depend on long chains of specialized work. No single workshop can stand in for an entire planet's factories. Health brings a similar problem. A small clinic may handle injuries and common illness. It may not handle every cancer, rare infection, difficult birth, or failing organ. Specialists take years to train. Medical equipment wears out. Drug ingredients expire. Even a settlement with excellent doctors could face a case that Earth once solved through thousands of hospitals working together. And children change the calculation. A population must be large enough to avoid harmful inbreeding across generations. It also needs enough adults to teach, repair, farm, govern, and care for people who can't work. We don't yet know the smallest population that could do all of this in a closed world. The answer depends on technology, stored embryos, contact with other settlements, and how much risk people accept. None of this proves that settlements beyond Earth must fail. It shows that surviving a disaster and building a self-sustaining society are different achievements. The first may need shelters, supplies, and trained crews. The second needs enough people and machinery to replace the web of support we barely notice here. So the choice isn't between certain doom and a triumphant new civilization. It's between degrees of dependence, each brought down slowly. How much of Earth's living system and industrial memory would a settlement need before it could truly continue alone? Calling another world a backup Earth makes it sound like replacing a phone. Keep the important files, buy new hardware, and carry on. But Earth isn't one object we know how to copy. It's a working arrangement among air, oceans, soil, microbes, machines, and billions of people. Most of that arrangement has never had to fit inside a launch vehicle. That changes the scale of the plan. A settlement on Mars could protect people from one class of disaster while remaining dependent on Earth for medicine, electronics, tools, or genetic material. Later, it might make more of those things for itself. Given enough time, it could become far harder to extinguish. That would be an extraordinary achievement. It still wouldn't be a second Earth. The difference isn't gloomy, it's clarifying. We don't need a flawless copy of our planet before people can live elsewhere. A small settlement can still teach us how closed habitats behave, how bodies adapt, and which supply chains are hardest to replace. Each lesson can reduce dependence. Each added capability can make human life less vulnerable to a single accident in a single place. But distance doesn't automatically create safety. A fragile outpost is another group of people to protect. A stronger settlement becomes a second branch of human life. And a truly independent world would require something much larger, not just passengers and equipment, but enough of Earth's biological and industrial web to keep rebuilding itself after failures. So perhaps the scale correction is the part worth carrying with us. Becoming a species that lives on more than one world isn't one heroic departure. It's a long transfer of skills, organisms, memory, and responsibility. There may never be a morning when someone can declare the backup complete. There may only be settlements that need Earth less with each generation, while Earth remains the one living world we already know how to inhabit. If another planet cannot replace Earth, what should becoming multiplanetary actually be for? So where does all of this leave us? A habitat away from Earth can keep people alive. It can carry air, water, food, power, tools, medicine, and stored knowledge. With enough preparation, it can survive failures that would once have ended the mission. That is a remarkable human achievement. But it is still a habitat. Earth does all those jobs at once, across an entire planet. Its air moves through oceans, forests, soil, ice, clouds, microbes, and living bodies. Water falls, flows, freezes, sinks, rises, and falls again. Waste from one living thing becomes food for another. Sunlight enters, heat leaves. Countless small exchanges continue without anyone checking a gauge. Inside a sealed home, every one of those exchanges becomes a machine, a stored supply, or a job. Carbon dioxide must be removed. Oxygen must be restored. Water must be cleaned. Food must keep growing. Heat must be controlled. Broken parts must be found and repaired. Nothing disappears because someone closed a hatch. That changes what survival means. The first crews would depend on supplies made on Earth. Later crews might make more of what they need. They could recycle more water, grow more food, and replace more parts. Given time, they might build homes that rely less on shipments. Less is not none. A settlement can become more capable without becoming a second Earth. It may last through a missed delivery, then several missed deliveries. It may survive for years, perhaps much longer. Each gain buys time and safety. None proves that the whole system can continue through many generations with no help from the planet that built it. And people bring needs that don't fit cleanly into engineering diagrams. Children must grow safely. Injuries must heal. Communities must settle arguments, teach skills, care for tired people, and make decisions when no rescue is coming. A working air system won't solve loneliness. A healthy crop won't settle a dispute. Survival requires both. So a backup settlement could protect human lives. It could preserve knowledge. It could give a small population somewhere to endure a disaster that makes part of Earth unsafe. Those are serious reasons to build one. They are different from replacing Earth. Replacement would mean carrying the work of a whole living planet into a closed world, then keeping it stable without that planet's help. We don't know how to do that. We haven't shown that a small human-made ecosystem can support a growing community across generations while repairing every failure from its own resources. That boundary doesn't make space settlement pointless. It makes the goal clearer. A lifeboat is valuable because it is a lifeboat. We don't ask it to become an ocean. Perhaps future settlements will surprise us. Their farms may become stronger, their recycling tighter, and their machines easier to repair. People may learn to live far from Earth for longer than we now expect. But every breath they will still carry a long inheritance, biology shaped here, tools built from knowledge gathered here, and lives made possible by a planet no habitat has matched. For now, every backup plan contains Earth inside it. In the seeds, in the microbes, in the metal, in the memories of rain, open air, and ground beneath your feet. Wherever we go, we won't begin again from nothing. We will arrive carrying home with us. And for tonight, home is still here. Good night.